Today what we're going to do is we're going to take what you know about acid-base chemistry and probably turn it around upside down and change a lot of things. So the first thing we're going to do is a review of what you know, mostly so that we'll show how it's consistent with what we do now, but you don't have to write down the first little bit. But the first little bit is what you know from a previous course, and that was based on definition proposed by Savant Arrhenius, or Arrhenius as some people like to pronounce it. And he said that an acid was something that increased the concentration of hydrogen ion, which we later looked at and referred to as a hydronium ion, slightly different, but that happened in water. And it would happen with something like this, where the acid molecule splits apart. The word we used was dissociates into the hydrogen ion, and in this case the chloride ion. And then that hydrogen ion would often connect with the water, react with the water to form the hydronium ion. So we could take those two reactions, put them together in some sort of net reaction, and say this, and then we have our hydronium ion directly. Well, then we said a base was something to increase the concentration of hydroxide ion, and hydroxide was something that's a standard polyatomic ion to begin with, so it really wasn't something we had to see where it came from. But we took a metal hydroxide, so sodium hydroxide in this case, and it dissociated into the ion, well, the two ions actually. So that's stuff we already know. But if we take a closer look at that H+, that hydrogen ion that Arrhenius talked about, what we're going to do is we'll see that as hydrogen starts out as a hydrogen atom with one proton and one electron, if it loses that electron, it's now a hydrogen ion, but it's also a bare proton. So we start using terminology that reflects the fact that a hydrogen ion is a proton, and you'll see some of that language coming up in a little bit. So when we write H+, we need to think about it as a proton. And again, that's going to be part of our language, but it's also going to be part of what we do in terms of the new definition. And the new definition was proposed by two individuals on opposite sides of the English Channel at roughly the same time. So we have Bronsted, who was a dashing young Dane, they've got some extra letters that we don't know about, and Lowry, who was a stodgy old Englishman, and quite proper in that sense. And they both came up with basically the same idea at roughly the same time, so they share the glory. And their definition says that an acid is a proton donor, something that can donate or give a proton. And a base is going to be a proton acceptor, but first proton donor. We'll take a look at that a little bit more closely. So you have an HCl, and that was our acid from the previous slide. And you'll see that as it moves from the reactant side to the product side, it loses an H+. So going from HCl to the chloride ion, lost a proton. Water, on the other hand, is going to be picking up a proton. We'll get to that in a minute. But going from the water to the hydronium ion, it has increased or gained one proton, an H+. So another example now here of a weak acid doing that kind of thing as well. And you can see if you follow the HBRO, the hypobromous acid, if you follow it through the reaction from left side to right side, you'll see that it's doing the same thing. It's giving up an H+, which we now know is a proton. Bases, on the other hand, which I was a little ahead of myself a moment ago, a base is a proton acceptor. So if we take a look at ammonia as our weak base, and it reacts with water, we can see that it forms ammonium and hydroxide ion. So we could even look at that with the Arrhenius definition and say that actually ammonia shows itself to be a weak base under that definition as well. But if I follow the ammonia, NH3, if I follow it through the reaction from the reactant side to the product side, I'll see that what's happened is it has gained an H+, which we know to be a proton. So it's accepted a proton. And likewise, the water has then lost a proton. Now, if you look at that definition of an acid, that actually starts to apply to water. And actually it applied in the previous set as well with the acids. So one of the things about this definition of an acid, the Bronsted-Lowry definition of an acid and base, is it's much more broad, and something doesn't have to have an acidic pH to behave as an acid if an acid is a proton donor. Likewise for a base. And another option for a thing acting as a weak base. Now if I look at reversible reactions, because we're all about equilibrium right now, if I look at reactions that are reversible, And if I take a look at the left side and right side and I start comparing them and I think about, okay, well, on the reactant side right now, I would have my hypobromous acid. Well, I didn't even call it an acid. I would have that thing which is able to donate a proton. And then the water is the thing that's able to accept a proton. So I have my acid and my base on the left-hand side. If I now look at the product side, if I look at the right-hand side, and I think about it as being able to react and form the things on the left, make sure I got my lefts and rights going right, then the hypobromite ion could, working its way back to the reactant side, could accept a proton. And the H3O plus could donate the proton. And we actually know that hydronium ion, that H3O plus ion, that is the, let's say, the active ingredient of an acid. So I have an acid and a base on both sides. And if I kind of follow that through the reaction, I can see that the acid and an acid on the left pairs up with a base on the right, and the base on the left pairs up with the acid on the right. And if I were to do a similar thing with a weak base, I would identify the base. I would identify the water as behaving as the acid. And on the opposite side, on the product side, I would have the opposites. So again, I would have a base pairing with an acid in terms of its identity. And the acid, or the thing that behaves as an acid, becomes a thing that can behave as a base. So what we do with that is we talk about conjugate pairs. And a conjugate pair is two things that exist in the same reaction. One is a product, one is a reactant. But more than that, they are different by one proton. So in other words, the HBRO, hypobromous acid, is the acid, and it's the thing that it becomes when it loses a proton, bromite ion, is the conjugate base. And if I look at the reaction going left to right and kind of work my way back and forth through it, I'll see that that thing accepted a proton if it works its way back to the reactants. Water, on the other hand, started out behaving as the base, but it turned into something that could behave as an acid. And likewise in the second reaction, similar kind of thing. I have well, in this case, I guess a base-acid conjugate pair and an acid-base conjugate pair with the water. Now, when we talk about acid-base conjugate pairs, we don't really worry too much about the order, in the sense that if I look at the ammonia and the ammonium and I said that was an acid-base conjugate pair, that's okay. Now, we don't have to worry about, oh no, it's a base-acid conjugate pair. They're a conjugate pair. One is an acid, one is a base. We need to know how to recognize which one is likely to be which, but we don't need to worry about being nitpicky with the terminology. Okay, now you notice that water is doing some weird things. Water was behaving both as an acid and as a base. We give that the name, or the term, amphoteric. And amphoteric just means that it can donate or can accept a proton, depending on what it's mixing with. If it's mixing with something that's more acidic, it'll force it to be a base. If it's reacting with something that's more basic, it'll force water to be the acid. And that's really all there is to it in terms of which one is it going to be. That leads us into something called autoionization, which is a big term, big word that just means it'll ionize itself, which is actually pretty important. And it also will perhaps answer a question that we would have had in a previous course about the behavior of water. So if I take two water molecules and I collide them together, and they collide with the right energy and the right orientation and all that other stuff, what can happen is one of those water molecules will pull a proton away from the other water molecule. So you'll end up with, all by itself, without an additional acid being added, you'll end up with some hydronium ion and hydroxide ion. Now you'll end up with a very, very, very tiny amount. So tiny that if you multiply the concentration of hydronium and the concentration of hydroxide in an equilibrium constant, and we call it Kw because the equilibrium constant for that, for the water, autoionization of water, you end up with 1 times 10 to the exponent negative 14, which doesn't look all that big of a deal right now until we think about that as 0.13 zeros and then a 1 moles per liter. Sorry, not moles per liter, because that's the constant. We don't have to worry about the units. In a neutral solution, and we know this already sort of, but in a slightly different way, in a neutral solution, of course, the amount of hydronium and the concentration of hydroxide will be the same. And that'll be about 1 times 10 to the exponent negative 7. So decimal 6 zeros, 1 mole per liter. Now, we know that a neutral solution has a pH of 7. And I know if I had the concentration of hydronium, I could calculate the pH. That's where it comes from. Now, as I add acid, of course, the concentration of hydronium is going to go up. The concentration of hydroxide is going to go down. And so that it always maintains that constant of 1 times 10 to the exponent negative 14 on the kW. We'll come back to that in a little bit more detail another time. By comparison, though, water, if you were to look at the concentration of water, pure water, it's about 55, 55.6, 55.5 repeating, but it's much, much larger. The point is, only a very, very tiny few molecules of water are going to be undergoing this autoionization process. And when we write it, we kind of forget that there's billions and billions and billions or more molecules of water, and only a couple are doing this. 1 times 10 to the exponent negative 7 moles per liter. That's not very much. Now, we have, on some of those examples that I've used, I've had a straight arrow. In some of them, I've had a reversible arrow. When do we use one-way arrows? When do we use equilibrium arrows? There's a short answer and a long answer. We're going to do the long answer first, and then I'll give you the short answer. So, when we're talking about strong acids, these are acids that have 100% dissociation. So if I were to take, represent an acid like that, a proton with a other thing, and I had a bunch of them, if I were to take those things and dump them into water, make a solution out of them, every single last one of them would dissociate, 100% dissociation. And we know that there are 6 strong acids, and they would all have a similar reaction, dissociation reaction, as what you see below the beaker there. Those 6 strong acids are the ones that we would use the straight one direction arrow. Oh no, one direction, one-way arrow. Okay, for weak acids, they have less than 100% dissociation, and they're usually a lot less than 100% dissociation. For them, if I were to take the similar 5 molecules of now some weak acid, I know it looks the same, but it's not the same, some weak acid, and I were to do the same thing, dump them into water, make a solution out of it, I might get one to dissociate because partial dissociation will happen, but most of them will not. Now, whether it's 5 to 1, 4 to 1, or whatever, it doesn't really matter because that's unique to each individual acid. But the point is, most of them are not dissociated. So then we have to write the equilibrium arrows to say that that reaction is not complete, that that reaction is also in dynamic equilibrium, that every once in a while another one might dissociate, but then one that was associated might recombine to form the original molecule. Okay, short answer. We're doing a reunion on equilibrium, so we're pretty much doing equilibrium arrows all the time. So I could have done it that way. Yeah. Weak acids. Ooh, the list for weak acids is really, really, really long. So let's make it easier. If it's not one of our 6 strong acids, it must be a weak acid. And chances are, if you're seeing it during this course and during the time that we're doing this stuff, it's probably a weak acid. Not all of them, perhaps, but most of them are going to be. Know those 6 strong acids. Sometimes, just to kind of make our work easier as we're doing this, we'll call it HA. So H, as our proton, plus some other anion that'll become the negative charge. Okay, bases. We've been talking all about this about acids, power bases. Well, bases are, they're similar, right? They're going to have equilibrium, and they're going to have equilibrium constants and formula and all that other stuff. They're going to find the pH. We'll talk about those in a little bit more detail and the sort of the things that we need to do for bases, but we have strong bases. And the list of strong bases is kind of a short one. It's group 1 and group 2 hydroxides. Now, here's the thing about group 2 hydroxides, or any hydroxide really. A lot of them are not very soluble. Group 1 hydroxides are pretty soluble. We can count on that. Group 2 hydroxides, not so much. Calcium, tiny bit. Barium hydroxide actually dissolves pretty well. But a lot of them aren't so good for dissolving. The little bit that does dissolve dissociates 100%. So, weak bases, these are going to be a little bit different, and they're going to be much more interesting in a way because the variance is we'll get there. It's just, there's a lot more variance to how something that can behave as a base rather than something that can behave as an acid. But yeah, so there we have a less than 100% dissociation. And then a lot of them start to look like this, where we've got carbon involved in it. And what you'll notice is that the first one with the ammonia and the next one that's not ammonia It's methylamine if you really want the name of it. But we start to throw carbon groups onto it. Okay, and then we start to get bases that way. So, a bit of a whirlwind, but the big thing is making sure we know how to recognize acid-base conjugate pairs. They are different by 1 proton. That's it. And once we get into class, we'll start doing the equilibrium expressions, and we'll start figuring out how we can actually find pH of a weak acid. And it'll be glorious. Talk to you in class.